In the last lecture, we were discussing physical interpretation of the terms in the spherical harmonic expansion for the temperature field, the non-axisymmetric spherical harmonic expansion in a spherical coordinate system. T is equal to summation n is equal to 0 to infinity, summation m is equal to minus n to n, a n m r power n plus b n m by r power n plus 1, okay, p n m of cos theta e power I m phi. Okay. And we showed that for n is equal to 0 and m is equal to 0, the temperature field corresponds to a point source of energy at the origin. Okay. Okay. And if you are observing at some observation point x, right, then the temperature field is given by T is equal to q by 4 pi k into the magnitude of x. Okay. The temperature field is proportional to 1 over r, for r becoming large compared to 1. Okay. Okay. N is equal to 1, m is equal to minus 1, 0, 1. Okay. Solution corresponded to a point source q and a point sink minus q, okay, observation point x, okay, separated by distance L, which is small compared to x. So, L is much smaller than x. The temperature field was equal to q L by, okay, into k r cubed. Okay. This, as you know, we had done it by an expansion of the superposition principle. Okay. We had used the superposition principle and done an expansion in the limit where L is much smaller than x. And I showed you that you will get 3 solutions. One is if the separation is along the z direction, you will get QLZ by 4 pi k r cubed. If the separation is along the x direction, you will get QLX by 4 pi k r cubed. And if the separation is along the y direction, you will get QLY by 4 pi k r cubed. In general, this can be written as Q into L dot x. Okay, that is the general solution. Okay. And then we were discussing the point quadrupole. Okay. And for that point quadrupole, we had considered one particular case, n is equal to 2. Okay. M of course can go from minus 2, minus 1, 0, 1, 2. And for the particular case where it was 0, I had shown you that this is equivalent to source at plus L by 2 and minus L by 2 and a sink at 0, okay, of strength 2q, in such a way that if you go sufficiently far away, the net source is 0 because you have 2 sources of strength q, one sink of strength minus q. So, the net source is 0. The net dipole is also 0 because from the source to one of those sinks, okay, you have a dipole moment this way, to the other one you have a dipole moment in the opposite direction. Since they are equally separated, the net dipole moment is also 0. Okay. And if you look at an observation point here x, okay, we had got the solution for that. The temperature field is equal to q L square by 4 pi k, okay, into 3 z square minus r square by 4 r power 5. Okay. It can also be written as q L square by 4 pi k into 3 cos square theta minus 1 by 4 r cubed. Okay. It is obvious that this is proportional to 1 over r cubed for all r becoming large. Okay. Source, the temperature decreases as 1 over r. Dipole, it decreased as 1 over r square. For the quadrupole, it decreases as 1 over r cubed. Recall our expansion. Okay. T for n is equal to 2, okay, and m is equal to 0. This will be A20 r square plus B20 by r cubed, okay, into P20 of cos theta. Okay. And when we had derived the Legendre polynomial expansions, I had told you that P20 is equal to half of 3 cos square theta minus 1. Okay. I told you that P20 is equal to half of 3 cos square theta minus 1. Okay. So, you can see the equivalence here, 3 cos square theta minus 1 and P20, 1 over r cubed and 1 over r cubed. Okay. So, this term for n is equal to 2 and m is equal to 0 corresponds to the quadrupole, which is axisymmetric and which is aligned along the z axis, okay, and which is aligned along the z axis. Okay. So, this arrangement of sources and sink correspond to one particular realization of this quadrupole. Okay. There are 5 such, n is equal to minus, m is equal to minus 2, minus 1, 0, plus 1 and plus 2. Okay. And for m is equal to 0, this is the configuration. What about the others? Okay. What about the others? Okay. Yeah. Okay. Now, you have 4 other quadrupole moments. Okay. So, I will just write down, I will not go through the details of the derivation, I will just write down how the sources and sinks are distributed in each case. Okay. And to keep it simple, I will plot the arrangements in an 2-dimensional axis. So, first one is the quadrupole. So, this quadrupole is called phi z square. Okay. Okay, it is called phi z square because you have the sources and sinks separated along the z axis. Okay. You have 4 others. Okay. One is phi x y. Okay. This one is 2 sources. So, in the x y plane, okay, looking from above in a 2-dimensional x y plane, you have sources located at, okay, 0 plus or minus L by 2 root 2, okay, plus or minus L by 2 root 2. Okay. That is, the sources are at these 2 locations, okay, at a distance L by 2 root 2 from the origin, and the sinks are at the locations, okay, 0 plus or minus L by 2 root 2 and minus or plus L by 2 root 2. Okay. This is x y, so it should be x and y. So, let me just, this is not correct. The source is at plus or minus L by 2 root 2 plus or minus L by 2 root 2 0, okay, and the sinks are at plus or minus L by 2 root 2 minus or plus L by 2 root 2 0. Okay. So, the sources in the first and third quadrant, the sinks are in the second and fourth quadrant, each one separated by equal amounts. In this case also the net source is 0, 2 sources and 2 sinks, all equal strength Q. Dipole is also 0 because you can see that one dipole moment is in this direction, the other dipole moment is in the opposite direction. If you go sufficiently far away, the net dipole is equal to 0. Okay. There are 2 other arrangements which are in the x and z axis and the y and z axis. Okay. So, okay, in the xz plane and in the yz plane. Okay. xz, this goes by the name phi xz. Okay. In the xz plane you have 2 sources, and 2 sinks. Okay. This is the second one. Okay. And this one, the source will be at plus or minus L by 2 root 2, 0 plus or minus L by 2 root 2, and the sink will be at plus or minus zero minus or plus L by 2 root 2. Okay. Okay, so that is the number 2 and number 3. Okay. The fourth solution is in the yz plane. Okay. Once again, you have 2 sources and you have 2 sinks. Okay. This goes by the name phi yz, and this has sources at 0 plus or minus L by 2 root 2 plus or minus L by 2 root 2, and the sinks are at 0 plus or minus L by 2 root 2 minus or plus L by 2 root 2. Okay. So, that is number 2, 3 and 4. And finally, you have one more, okay, which is in the xy plane. It is called phi x square minus y square. 2 sources along the x axis and 2 sinks along the y axis. Okay. And the sources and sinks are at and the sinks are at 0 plus or minus L by 2 0. Okay. So, these 5 arrangements give rise to quadrupoles. Okay. These 5 arrangements of sources and sinks give rise to quadrupole moments. These linear combinations of these gives you the second order terms in this distribution. Okay. So, linear combinations of these gives you the second order terms. Okay. For n is equal to 2, m is equal to 0 is this one phi z square. N is equal to 2, m is equal to 1 gives you phi x z and phi y z. Okay. N is equal to 2, m is equal to plus or minus 1, and n is equal to 2, m is equal to plus or minus 1. So, linear combinations of n is equal to 2 and m is equal to plus or minus 1 give you phi x z and phi y z. Linear combinations of n is equal to 2, okay, m is equal to plus or minus 2, and n is equal to 2, m is equal to plus or minus 2. Linear combinations of these two give you the phi x y and phi x square minus y square. Okay. So, those are the quadrupole moments. So far, we have talked only about these terms here. Okay. So far, we have talked only about these terms here. Okay. What about these terms? Okay. So, these decaying harmonics we had got in terms of point source, point dipole and point quadrupole. What about the growing harmonics terms? Okay. So, what are the growing harmonics? Okay. So, for the dipoles, okay, the temperature is of the form A r plus B by r square into cos theta, okay, for okay. And you can see that this A r cos theta is just equal to A z plus B by r square cos theta. Okay. So, the growing harmonics are just linear in r, okay, they are just proportional to r. Okay. So, just as in the case of the decaying harmonics, okay, for the point source, in the z axis you had a point source and a point sink separated by distance L, which is much smaller than the distance x to the observation point. Separated by distance L, which is much smaller than the distance x to the observation point. In a similar manner, this growing harmonic basically corresponds to the heat conduction between a hot surface and a cold surface, okay, where the temperature varies linearly with z. Okay. So, the temperature in this case varies linearly with z. Okay. Okay. And the heat flux lines are straight lines going between these two surfaces. Okay. The heat flux lines are straight lines going between these two surfaces. Okay. So, that is what is the inverse of this dipole, which is a source and sink separated by an infinitesimal distance such that the separation is much smaller than the distance to the observation point. Okay. So, that is the inverse of this, a constant linear temperature, a constant temperature gradient. Okay. Similarly, the growing harmonic corresponding to this, okay, in the x direction. So, okay, would be a source and sink separated in the x direction. Okay, such that you have heat flux lines going from the source to the sink. Okay, such that you have heat flux lines going from the source to the sink. The temperature gradient is along the x direction. Okay. Okay, the temperature gradient is along the x direction. It should be the other way because temperature should be higher here. Okay. And similarly, in the y direction. Okay. 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 This corresponds to the growing harmonic corresponds to this. Okay. Such that you have heat flux lines that go in this direction. Linear temperature gradient in the y direction. So, that is the meaning of the growing harmonics. Okay. For the quadrupole moments, the growing harmonics, I will not go through the details here, I will just leave it to you to do it on your own. Okay. So, those are the equivalences between the terms in the expansion, in the spherical harmonic expansion, and the interpretation in terms of the source, the dipole, the quadrupole, etc. Okay. Okay, if you have a point source, a point dipole, point quadrupole, etc., that is the meaning of the terms in the expansion. N is equal to 0 is just a point source, n is equal to 1 corresponds to a dipole, source and a sink in such a way that net source is 0, temperature decreases as 1 over r square, okay, and as r goes to infinity. Okay. So, that is a point dipole, n is equal to 1, m is equal to minus 1, 0, plus 1, there are 3 of them. Quadrupole, there are 5 of them, m is equal to minus 2, minus 1, 0, plus 1, plus 2. 2 sources and 2 sinks in such a way that the net source is 0, the net dipole is 0. Okay. So, that is the quadrupole moment. Okay. And then you will have 4 sources and 4 sinks such a way that the net source, dipole, quadrupole is 0. N is equal to 3, m is equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. You will have 7 such solutions, okay, and so on. Okay. So, that is the solution for a series of point sources, point dipoles, point quadrupoles, and their equivalence to the temperature field in the spherical harmonic expansion obtained by separation of variables. I will briefly go through what is called a distributed source. Okay. What if we did not have a point source, but something that was distributed over some volume? Let us say there is an exothermic reaction going on, and based upon the reaction rate you have a certain source energy generated per unit volume per unit time throughout the domain. Okay. In that case, how do you find the temperature field at a given location? Okay, so that is the next question. The temperature is K del square T plus this Q, which is a function of position, is equal to 0. Okay, if it is uniform, it could be a uniform temperature generation of heat per unit volume per unit time. In this case, how do we solve the problem? Okay. So, if I had a distributed source, okay, for a single point source, I know that the temperature field, okay, I missed out the T here. For a point source, I know that the temperature field is equal to Q by 4 pi K R. Okay. Whereas this is a volumetric source, it is a source per unit volume per unit time. Okay. So, within this volume. Okay. What you can do is divide this volume into a large number of infinitesimal volumes. You can divide this into a large number of infinitesimal volumes. Okay. So, this entire volume V is divided into a large number of infinitesimal volumes, okay, which I will call as delta V1, delta V2, etc., delta Vn. Okay. Since these are infinitesimal volumes, I can consider the energy source as, okay, energy source in each volume is equal to Q at x1 prime delta V1. Okay, I will call this, I will use a prime for the volume. Okay, so, to avoid confusion later. Q at x1 prime delta V1 prime, okay, times delta of okay, okay. Note that QV is the energy generated per unit volume. QV at the location x1 prime is the energy generated per unit volume at the location x1 prime. QV multiplied by delta V1 prime is the energy generated, total energy generated within the volume delta V1 prime. That energy generated times delta of x minus x1 prime is the energy generated per unit volume. Therefore, the total energy that is generated within a volume, I am assigning it to that center point x1 prime as a delta function at that center point x1 prime. Okay. So, total energy generated within the volume is being assigned at the location x1 prime at the center of the volume, and it is assumed to be a delta function at that center. Okay. So, this is equal to plus QV at x2 prime delta V2 prime delta of x minus x2 prime plus etc. Okay. For this particular, okay, delta of x minus x1 prime times QV at x1 prime times delta V1 prime, for that the temperature will be equal to 1 by 4 pi k into QV delta V1 prime delta V1 prime divided by x minus x1 prime. Okay. So, that is for the first volume. Okay. And then for the second volume QV at x2 prime times delta V2 prime by x minus x2 prime, okay, plus etc. Okay, plus QV at xn prime delta Vn prime by x minus xn prime. Okay. that is for each of these individual delta functions assigned at the center of their respective volumes of strength QV times the volume, okay, because QV times the volume gives you the energy generated per unit time, of strength QV times the volume. I found out the temperature due to each of these delta functions, summed them all up. Okay. And in the limit as these delta V1 prime, delta V2 prime etc. go to 0, okay, this summation can be replaced by an integral. Okay. Is equal to 1 by 4 pi k integral dv prime qv of x prime divided by x minus x prime. So, that is the temperature field due to a distributed source. Okay. That is the temperature field due to a distributed source. Okay. So, this is the observation point x. Okay. This is first point is x1 prime, this is x2 prime etc. Source points are written with primes, observation point is written without a prime. Okay. So, the observation point is written without a prime and the source point is written with a prime. Okay. Therefore, based upon this I can find out what is the temperature field due to a distributed source, okay, as the integral over the volume of the energy generated per unit volume per unit time at a given location divided by x minus x prime, and of course, there is a 1 over 4 pi k outside. Okay. This is the observation point, okay, and this is the source point, and you are integrating over all locations for the source point. Okay. So, that is how you can find out the temperature field due to a distributed source. Okay. And you can get the flux as well. Okay. So, that is also quite straightforward. We know that the flux q vector due to a point source is equal to q into x minus xs by 4 pi k into x minus xs the whole cubed. For a distributed source, the expression is just q is equal to integral dv prime q of x prime into x minus x prime by 4 pi k into x minus x prime the whole cubed. So, that is how you calculate the temperature field for a distributed source. In the next lecture, I will discuss a particular example of calculation of this temperature field due to a point source and due to a distributed source, and then we will go on to looking at what do we need to do to apply boundary conditions. Okay. So, I will continue this in the next lecture. I will see you then.